In this question, a fictional scientist is investigating a reversible reaction involving fictional substances R3L, GX, R2X, and G3L2 at a temperature of 387 Kelvin and a pressure of 1 atm. So we can see we've got our equation there. We've got our reversible reaction arrow showing the reaction can go forwards and backwards. Our goal is going to be writing an expression for the equilibrium constant K and then calculating the equilibrium constant K. So let's head to our reference sheet. Here's our equilibrium constant. So we're told for a reaction at equilibrium with this equation, here's our equation for K. So you can see in the expression for K, we have the concentrations of our products and reactants in a fraction. On the top of the fraction, we have the concentrations of our products, which are uppercase C and uppercase D. On the bottom of our fraction, we have the concentrations of our reactants, which are uppercase A and uppercase B. However, we can also see that those concentrations are to the power of the coefficients from the chemical equation. So if lowercase c is the coefficient of uppercase C, we've got the concentration of C to the power of lowercase c. And we've got the same for D, A, and B. So to summarize, in our expression for K, the top of the fraction has the concentrations of our products to the power of their coefficients divided by the concentrations of our reactants to the power of their coefficients. However, there's an important note here. Only gases, shown with a G, and solutions, shown with an AQ, are included in the equation. So if we have solids or liquids, those are not going to appear in our equilibrium constant equation. Okay, so in this equation, we're going to have the concentrations of our products to the power of their coefficients divided by the concentrations of our reactants to the power of their coefficients. But it's only going to be things that are aqueous or gas, not solids and liquids. So let's start by doing our products. So in the products, we have R2X. It's aqueous. That means it is going to appear in our K equation. So let's write that down. We've got the concentration of R2X. It also has a coefficient of 3. So that means the concentration of R2X is going to be to the power of 3 in our K equation. Then we're going to multiply that by our next product, which is G3L2, which is aqueous, meaning it's a solution. Because it's either a gas or a solution, that can appear in our K equation. So we're going to have the concentration of G3L2. And the coefficient for here is just 1. We've only got one of them. So that would be to the power of 1. But remember, to the power of 1 is just the same as the thing itself. So we don't need to include that. Okay, that's all our products done. Now in our reactants, we've got R3L in gas form. Aqueous or gas, those are allowed in our K equation. So this is going to show up. So we've got R3L. And it's going to be to the power of the coefficient. The coefficient here is 2. So that's going to be squared. Multiplied by our other reactant. Now here we've got GX, but it's a liquid. Liquids do not appear in our equilibrium constant equation. So that is not going to appear because we have liquid. So I can either put a 1 there to show it's not appearing, or I can just leave it blank. Those mean the same thing. Okay, so there's our equation. So let's use our drop-down box to find that. We've got R2X cubed times G3L2 on the top of our fraction. On the bottom, we have R3L squared on its own. So writing our equation, all it involves is looking at our products first. Those are on the top of our equation. We have the concentration of each product to the power of its coefficient, and we multiply them together. but only for things that are aqueous or gas, not for solids and liquids. We then do the same for the reactants, and they go on the bottom. Awesome, so we've done the hard part, which is getting our expression for K. Lastly, we need to calculate K, the equilibrium constant. And we're given, at equilibrium, the concentrations of those three substances we have in our K equation. R3L is 0.151, R2X is 0.322, and G3L2 is 0.281 molar. So we can go ahead and put those numbers into our equation. So R2X was 0.322 molar. So 0.322 molar to the power of 3. Then we've got G3L2, which is 0.281 molar to the power of 1, divided by R3L, which is 0.151, and that's to the power of 2. So if we put that all into our calculator, we're going to get out a value for K of 0.412. And there is no unit required for the equilibrium constant. So let's go ahead and fill that in here. We had 0.412 for our equilibrium constant. I'm just going to make a note here to say no unit required. Finally, we're asked, are the products or reactants favored at equilibrium for this reaction? And since our K value is 0.412, it's less than 1, which means our reactants are going to be favored at equilibrium. So in these questions, first we're finding the equilibrium constant expression. To do that, we take the concentrations of our products to the power of their coefficients and multiply those together on the top of our fraction. We do the same for the reactants on the bottom. However, we do not include any products or reactants that are in the solid or liquid state, only solutions and gases. Then, to find an equilibrium constant, all we do is plug in our numbers for our concentrations when the system is at equilibrium, and that's going to get us out our value for K, the equilibrium constant, at that temperature. If K is less than 1, reactants are favored at equilibrium. If K is greater than 1, products are favored at equilibrium. If K is equal to 1, then neither products nor reactants are favored at equilibrium.